So I'm just going to go back for a minute. We collected data about walking in the hallway, right? So just to kind of go back and summarize, can someone tell me actually, I might just take, can I steal yours, Anya? Because you had a nice graph and I didn't actually collect data. This would help both Liliana and anyone else who might have missed this activity. So Anya walked in the hallway. To go 10 feet, it took her 2.5 seconds, and then 4.9 seconds to go 20 feet, 8.5 seconds to go 40 feet, and about 20 seconds to go 100 feet. So she connected her 4 data points, and it formed a pretty straight line. So if you were walking at a consistent pace, it really should be a linear relationship. It takes you so many seconds to go each foot. So if you were a little bit off on one of your data points, there's just some experimental error. You had to walk a certain pace, your partner had to time you, you had to record the data correctly. If you're off a little bit, that's okay. We're just leaning towards, hey, what is a type of linear relationship? Walking speed or car speed over time should be linear if the pace is the same over time. Obviously, if you walk faster, then your line might be like this, and then you walked faster, and then it might go like this, a steeper slope if you walked a different pace. And then I'm going to show you her part 2, because similarly, she had some pretty good data for her bouncing ball. So what we did is we dropped the ball from 60 inches in the air, and then we let it bounce once. So you should have collected 3 trials and had an average of the 3 trials for the one bounce, just to help us with our experimental error, right? So her first bounce average was 48, and then for 2 bounces, 39, and then she got right around the same for the 3rd and 4th bounce. So her data, if you graph the 60, it should actually start to curve. Some of you had that it was kind of a straight line. I get it. It's experimental error. It's hard to catch the ball exactly. But in a perfect world, it would have started to look like this. So an exponential decay curve. If yours doesn't look like that, that's okay. We're talking about it now. We're just generalizing. And I have something to look at in a minute. But it should have been kind of exponential decay over time. And then the third one, the one that I was just talking about, was the height of the ball through the air. Thank you so much. So the height of the ball through the air, part 3, is the one I kind of just plotted up on the board, but just for the sake of a video, if you had your horizontal distance and you had your height of your ball, right? If I'm tossing the ball through the air, gravity brings it down at the same rate that it's going up. So it's a symmetrical graph. Projectile motion has a symmetrical graph. And we're actually going to do some catapults later in the year when we talk about quadratics, because they always have this parabola-looking graph. So just those 3 situations, we're just meant to introduce you to, these are the 3 big functions we're studying this year: linear, exponential, and quadratic. And we're going to go into linear next unit. So this unit is just, what are the big 3? Can I recognize those big 3 sets of functions so that when I'm looking at data, I know what kind of function that is? It would do you no good to do a linear model of this, because a linear model is going to send you off in the wrong direction. You're going to miss all these data points. So as a good mathematician, you have to know what model you're using. You have to be a little smarter than your calculator. And I'm going to show you today how to do a linear regression on your calculator. So I kind of already summarized these, but let's just wrap this up. The one that shows the linear relationship really should have been number 1, the walking speed. And it says, if any of the parts have a different relationship, what type of model? I kind of already said them for you. So number 2 should have been exponential, and number 3 should have been quadratic. And if you're not there yet, that's okay. So it's just kind of some experimental data, bringing back some Algebra 1 vocabulary. Can anyone think of other types of relationships that might be linear? See see if you can come up with any other situations that might be linear. We just talked about Devin's weekend. I don't know if all of your jobs are, you get an hourly wage, but if you work 20 hours, do you know how much you're going to get paid? And if you work 17 hours, do you know how much you're going to get paid? Unless you're working on tips, right? There's an hourly wage and then tips are kind of your bonus. But hourly wage is a linear relationship. It should be anyway, unless you're getting cheated. And then, overtime is a different hourly wage. So if you get paid overtime, it's still a linear relationship. It's just a steeper rate. You're getting more per hour. How did dog walking work? Did you just get a flat rate for you're going to watch the dog and you're going to get paid X, right? So that's not a linear relationship. He might have spent 4 hours or 10 hours with the dog. She was going to pay him X regardless, right? That's kind of how salary works too. You're going to get paid this much for the year. You might put in some hours, some weeks. Like if you're a CPA during accounting time, you're putting in 60-hour weeks in April. But during the summer, you might be only putting in 20-hour weeks when it's not tax season, things like that. Any other linear relationships? One I think of is for children, there are growth charts. And so certain things about your growth over time is linear when you're a child, like they're tracking your growth over time, your height. Obviously that tapers out because we're not growing, half an inch every year anymore, some of us, but maybe growth of certain things, people's relationship between their wingspan, so your arms out to your side, your wingspan and your height are actually related to each other. So someone who is a little bit shorter has less of a wingspan than someone who's taller. Anyone watch the Olympics this summer? Do you remember the famous swimmer Michael Phelps from like 4 years ago? He was very tall. His wingspan was humongous. And that's what allowed him to pull through the water and set all those gold records, right? So the taller you are, you do have an advantage of a wingspan. That's a linear relationship. Someone who's shorter, your arms just aren't going to be as long. So there are different linear relationships to think about. Okay, the last thing I wanted to leave you with, I'm not going to be assessing you on rebound ratio this unit, but during our exponential unit, you're going to see it again. So did you know that a ball bouncing, right, it can have a higher rebound ratio? So this is a pretty bouncy ball. You see how high that's bouncing each time? This one has a pretty good rebound ratio. That ping pong ball that I lost doesn't have as good of a ratio because it's a cheap ping pong and it's like crap now. So, I mean, when you look at this one, it's dying pretty fast, right? So this has a much higher rebound ratio than this one does. But in and of itself, this should have a consistent rebound ratio for the red ball, and the white ball should have a consistent rebound ratio for the white ball. So I just want to show you what a rebound ratio is. And so I'm going to have you each do your own rebound ratio based on your experimental data. So I'm going to do one for you first. So Leslie, do you remember which ball you used? Can I steal your data just to show them an example of, so this was Wesley's basketball. So if you worked with Wesley, or you can steal this or do it yourself in a minute, but his drop height was 60, bounce 1 was 36, bounce 1 was 36, bounce 2 was 23, 23, 15, 10, oh wait, 15, 10. So I just want to show you where you're going to set up your numbers. To get the first rebound ratio, so in his chart went 60, 36, 23, 15, and 10. To get the first rebound ratio, you take the bounce divided by the starting height. So on my calculator, I'm going to take 36 and divide by 60 and get whatever I get. You should have a calculator maybe in your basket next to your desk, and if not, there's a few in the back corner, but you're going to need a graphing calculator. You could do this part on your phone, but for what we're doing next, you need a graphing calculator. So 36 divided by 60, that has a rebound ratio of 0.6. You're going to do this with your own data in a minute. So the first rebound ratio for his basketball was 60 or 0.6. So then for your second rebound ratio, you're going to take the second bounce divided by the first bounce, 23 divided by 36. So that's a 0.64 rebound ratio. That's pretty consistent, right around 0.6 still. And then let's see, his 15 divided by 23, 0.65. That's still pretty consistent in the 0.6 range for a rebound ratio. Some of you might have like 0.8, 0.8, 0.8. It should be around the same. So I'm doing 36 divided by 60. So you're going to take your bounce 1 and divide by your starting height. So here were my divisions. I did 36 divided by 60. Then I did the next two numbers in the chart. 23 divided by 36. 15 divided by 23. So each bounce gets its own rebound ratio. And how consistent you were, probably correlates with how close your rebound ratio was each time. Does it make sense what you do now? Right, so calculate them for your data. Does that make sense, what you're calculating? Yeah, right, so this one we talked about is probably a little bit off, but that's pretty good. If they're all right around 0.8, you did a pretty good experiment. And yours were around, they vary. So, if you found the average of those four, what was your rebound ratio? Find the average of those four, because that'll probably get you closer. You kind of have a low and a high, and the two that are pretty consistent. Why don't you, because I already did yours, why don't you find your average rebound ratio? So you add them up and divide by 4, and you can just steal the data that was on board. That's fine, you already did. Or you still heard data? No, the board data, that's good, yeah. So if you are a referee in a basketball game, do you ever see the referees drop the basketball from about shoulder height and just see how bouncy it is? A basketball could be overinflated, and they know, because they're experienced referees, if it's going to bounce above my waist, it might be too bouncy. It might be an overinflated basketball. Same thing in football, right? They overinflated the football during one of the scandals. I don't know, but you know what I mean? Because if it's overinflated, it's going to fly a different way, bounce a different way. Tennis balls. Did you ever notice that they come in those sealed packs of 3, and you have to like pop the tab? They're pressurized, right? Because a new tennis ball has a certain bounce ratio, right? A really old tennis ball, I'm sure that this is a really old one that I got out of my garage that's been through multiple winters and freezing temperatures. It's not going to have the same bounce as a new tennis ball. So when you play a game, you want to have a fair bounce. The ball should be consistent. So anyway, that's just to introduce you. What I wanted you to notice is it should be fairly consistent. And so this was the basketball 0.6. Which ball did you have, Anya, that your ratio was around 0.8? Did you, the what? Oh, she had the golf ball. Okay, so the golf ball is really bouncy, so it has a higher rebound ratio. Did anyone have a lower rebound ratio than this? 0.5s or 0.4s? Did anyone have the red ball? Yeah. What did you get for your kind of average, or what did you get each time? 0.7s or 8s? Okay, so I think the red ball then was probably even bouncier than the golf ball, based on Justice's measurements. Okay, it's a pretty bouncy ball. So the higher the bounce, the higher the rebound ratio, and the lower the bounce, like if you think about a bowling ball, right, it's going to have a pretty low rebound ratio. It's not going to bounce very much. What other types of ball do you think would not bounce very much, have a low rebound ratio? Think of some of the other sports. What? Pool? Oh, cricket. I don't even know what kind of ball that is. Is it similar to a baseball? I think a baseball has a pretty low rebound ratio. It's going to bounce a little bit, but not much. All right, so those are the big 3 types